Einstein's theory of special relativity is based upon two assumptions. They are extremely simple and yet very powerful. The first assumption, or postulate, is that the speed of light is a universal constant. What that means is that it doesn't matter what that light was emitted from, how fast it was moving, who observes it, or whatever. So, for example, if there's a car that's moving towards you, you will see the speed of light as being exactly the same as the person in the car. The second assumption is that the laws of physics are exactly the same in every inertial frame. An inertial frame, as you know, is one that is not accelerating. So, if you were to look at any physical law, let's say that of motion or of electromagnetism, whether you are on Earth or whether you are in a spaceship that's moving at some fantastic speed, you will deduce the same laws of physics. That is, their form will be the same. Now, these are very simple assumptions, but now let's see how much power they have by focusing on specific situations. Let's take a look at this railway platform with two men standing at the opposite ends. They have heavy balls in their hands, and the one at the left is going to throw his ball towards the person at the right, absolutely straight. The one at the right is simply going to let his ball drop straight to the ground. Now, of course, both the balls hit the floor at exactly the same time. And that's exactly what you would expect, because there was no downward component to the velocity. Now we'll assume that there are two people, everything else is exactly the same, but they're standing on a trolley pulled by a train at constant speed. Now let's play both of these animations together. Suppose that the people standing on the platform found that it took 3 seconds for their ball to fall to the ground. Well, the people on the trolley will also see 3 seconds for their balls to fall onto the trolley. But here comes the strange thing. The people on the platform will not see the ball on the trolley take 3 seconds to fall down. They will see it as a little bit more. And the funny thing is that the people on the trolley will say exactly the same thing. They will see the balls on the platform take a little bit more than 3 seconds to reach the ground. We are now going to deal with the phenomenon of time dilation, one of the most amazing predictions of Einstein's theory of relativity. Time dilation can be put across in several different equivalent ways. First, to a person on the ground, the clock attached to a moving frame appears to move slow. Another way of saying this is that time passes more slowly for fast-moving objects. You could also say that moving clocks run slower. To get an actual formula for time dilation, we'll need to remind ourselves how time is measured. So take this light clock, which we've seen before. There are two mirrors and a particle of light which goes between the two mirrors. Now let's call this distance between the two mirrors L. And so obviously the time that is taken by light to go from one mirror to the other is L over C. So the total time is L over C plus L over C, which is 2L over C. And this is what is called the proper time. So here we have a situation where the observer, Mr. Garfield, is at rest with respect to his clock. Or you could say that the clock and the observer are traveling together. That is what we call the proper time. Let's look at the same clock, but this time a moving one. From the point of view of this observer who is fixed to the ground, this clock is moving towards the right at speed, let's call that v. A photon that is released from the bottom mirror is reflected from the top mirror, comes back, and so forth. Now the photon moves towards the right at speed v. Let's now look at the trajectory of the photon. So suppose that it is emitted from this point, it moves up to this point, is reflected from the mirror, and comes back to this point. So this is the time that is taken to go and come back. Let's call that time t prime. So the distance, or rather the half distance from here to here, will be half of v t prime. This distance, of course, is L. L is the distance between the two mirrors. And so the distance that the photon actually has to travel will be L squared plus the square of this distance, which is 1/4 v squared t prime squared. The time, therefore, that is needed to go from here to the other mirror will be this distance divided by the speed of light c. And so, therefore, the total time, t prime, will be twice that amount, twice because it has to go up and come down. And let's take this distance, which is L squared plus 1/4 v squared t prime squared, and this has to be divided by c. Now let me take c on that side and square both sides, so I get c squared t prime squared is 4L squared plus 4 into 1/4 v squared t prime squared. And from here, I get t prime squared is equal to 4L squared divided by c squared minus v squared, which we can write as 2L over c squared into 1 over 1 minus v squared divided by c squared. And now from here we get t prime is 2L over c into 1 over the square root of 1 minus v squared divided by c squared. Now this 2L over c is exactly the proper time. And we had called this t earlier. This factor, 1 over square root of 1 minus v squared over c squared, will occur everywhere in relativity, and we give it the name gamma. And so what we found is that t prime is equal to gamma times t. That's the time dilation formula, and let's understand what this means. If you were traveling with the clock, then t is the time that it would take to go from the bottom mirror to the top mirror and to come back. So anyone traveling with the clock will see time t. Let's say that this time t is 1 second. The time t prime, on the other hand, is the time observed by this person here on the ground. Now let's look at this factor gamma. I'm running out of space, so I'm going to rewrite this over here. That's 1 over 1 minus v squared over c squared. And now since v is less than c, everything travels slower than light. Therefore, this 1 minus v squared over c squared is a factor which is less than 1, which means that this gamma will always be bigger than 1. On the other hand, if v is equal to 0, well then it will be equal to 1. Now let's say this clock was traveling very, very fast. So v was, let's say, 4/5 of the speed of light. In that case, gamma would be 1 over square root of 1 minus 16 over 25. And 25 minus 16 is 9. So this would be 5 over 3. So gamma would be something like 1.67 if the clock was traveling at this enormous speed. You can see that as v gets closer and closer to the speed of light, gamma becomes bigger and bigger. In fact, for subatomic particles, gamma can be 100, it can be 1,000, and it can even be bigger than 1,000. What that means is that if 1 second passes according to the person who's traveling with the clock, 1,000 seconds could pass for the person who is watching from the ground. This is why this is called time dilation. Time is passing slower as the clock moves faster. Here is a quick summary of what we've learned so far. First, the proper time, we call it t. This is the time seen by someone moving with the clock. And now this clock does not have to be a light clock. It can be any kind of clock. It can be an atomic clock. It can be a spring watch or whatever. Exactly the same laws apply to every kind of clock. This is the definition of the gamma factor that we saw. Clearly, if v is 0, then gamma is 1. And so for slowly moving objects, gamma is going to be very, very close to 1. But as v gets closer and closer to the speed of light, then gamma gets bigger and bigger. In fact, there is no upper limit to how big gamma can be. The most important thing that we learned was that if you take 2 subsequent ticks of a light clock, as observed from the ground, then that is gamma multiplied by the proper time. In other words, the time observed by someone moving with the clock on the train. Now, because gamma is always bigger than 1, therefore we see that the clock on the train appears slowed down when observed from the ground. But here is an apparent paradox. After all, who is moving and who is stationary? The person on the ground says that the train is moving, but according to the person on the train, the observer on the ground is moving in the opposite direction. In the early days of relativity theory, when people didn't know very much about it, some people tried to discredit the theory with what they called the twin paradox. Let's imagine 2 children born at the same time on Earth. One of them is going to stay on Earth, and the other is going to travel to a distant star which is 400 light years away, and then immediately head back. 1 light year is a huge distance. It's the distance that is traveled by light in 1 year, so that's the speed of light times the number of days in a year, 365, times the number of hours in a day, times the number of minutes in an hour, times the number of seconds in a minute. We'll call the speed of the spacecraft v, and beta is then defined as v over c. So this is a number that's always going to be less than 1 but can be very close to 1. In terms of beta, gamma is obviously 1 over the square root of 1 minus beta squared. Now let's take beta equal to 0.999, gamma is 22.36. The time taken by the spacecraft, according to the person who stays on the ground, is close to 800 years. So it took almost 400 years to go and 400 years to come back. On the other hand, the clock for the twin who had gone and came back was running much slower. When you divide 800 by gamma, which is 22.36, this is the number that you get, 35.8 years. So what that's telling us is that the twin who stayed on Earth died long ago, but the twin who returned was just 35.8 years old. The reason this was called a paradox was because wasn't it possible for the person who had gone on the spacecraft to have said, oh, the twin has gone off and come back, and therefore both situations should be equivalent? The answer is no, because both of them were born here on Earth, obviously at rest. Then the twin who went off into space had to accelerate very rapidly, go all the way across, and then change direction, and then come back. That means that the space-traveling twin was not in an inertial frame, and so therefore there is no paradox. The first twin was genuinely in an inertial frame, whereas the space-traveling twin was switching between frames and hence not in an inertial frame. Of course, interstellar travel is not possible as yet, but we can check time dilation using particle accelerators. Here is an example of one, a very big one, located in Switzerland and France called CERN. Beneath the ground, there is a very fast-moving beam of particles. These particles are moving almost at the speed of light. Let's look at this particle which is moving in a circular orbit. Now, this is an unstable particle, which means that after a certain time, it decays. But we see that it lives longer because of time dilation. Let me cook up an example that is actually not too far from reality. So take a particle that on the average lives for a millionth of a second. T is 10 to the minus 6 seconds. Now, this is the time that a particle will live in a frame in which it is at rest. In other words, if you were moving with the particle, then it would last this time, a millionth of a second. Now, suppose this observer over here sees the particle moving at speed v. And just to be definite, I'm going to take a value which is very, very, very close to the speed of light, 0.999999 times c. In other words, beta is this number over here, very close to 1. You can easily calculate gamma, and that works out to 1000. Okay, now let's see how far this particle will travel if it is traveling at this speed. That distance d will be v, but v is very close to c, so I'm just going to put 3 times 10 to the power 8 meters per second times the time which is seen by the observer, and that time is gamma times t. That's what we learned about the time dilation formula. So let me put now t over here, 10 to the minus 6 seconds. And this gives us 300 times gamma meters. Now, what that means is that if it was moving in a circle with circumference 300 meters, it would go around once if gamma was 1, but it'll go around 1,000 times if gamma is 1,000. Now, this is exactly what is observed, that if there's a particle which is moving with gamma equal to 1,000, for example, then it will go 1,000 times around, or in other words, it'll travel a distance which is 1,000 times greater. This is a fact that we see every day in our particle accelerators. Length contraction is another very strange prediction of the theory of relativity. It says that objects moving along the direction of motion become shorter. It's not that they seem shorter, but they actually become shorter. So, for example, if you have this rod, when it starts moving close to the speed of light, it becomes shorter, maybe half its length, maybe a third, more or less. All that depends upon its speed. Now, although this length here changes, it goes from long to short, however, the transverse size, that is to say, the width, remains exactly the same. It is only in the direction of motion that something becomes shorter. This is also called the Lorentz contraction. Here's an amusing animation of Lorentz contraction. A spaceship is moving at beta equal to 0.1 and the sign behind it is of normal size. But if the spaceship moves at beta equal to 0.865, that is to say 86.5% of the speed of light, then the Lorentz contraction is much greater. And if it's moving at beta equal to 0.99, then the Lorentz contraction is still greater. To get a formula for the Lorentz contraction, let's consider two parallel mirrors, this one and this one. And now note that they're placed vertically rather than horizontally. They are at rest with respect to this observer here. We'll call this distance between the two L. And this L is what we shall call the proper length. So this is the length in the rest frame. Now, if t is the time taken for a photon to go and to come back, then the proper length L will be the speed of light times the time taken to go one way. So t over 2. The proper length over here, proper time over here. Now note that in this case, we are not using these mirrors as a clock, but rather as a ruler. So the length now is to be defined in terms of the time. Now let's put the mirrors into motion. Both of them will be moving towards the right at speed v. According to the ground-based observer, the distance between the two mirrors will no longer be L. In fact, it will be something else. Let's call that L prime. A photon that is emitted from the left mirror will move towards the right mirror, arrive there, and be reflected back. Of course, the photon will be moving at speed c no matter whether it is observed by the ground-based observer or by one who is moving with the mirrors. Let's calculate the time as observed by the ground observer. We'll call that t prime. So t prime is the time observed by Mr. Garfield, or the ground observer. Now, we're going to separate this off into two parts. T prime will be the time taken to go from left to right, and then T2 will be the time taken to return. We'll calculate each of these separately. So let's take the first one. Suppose the photon is emitted from this point. Well, it goes a distance L prime. That's the distance between the mirrors. But this mirror has moved off a certain amount, and that's v times t1, the speed at which the mirror is moving times t1. And so t1 will be the total distance traveled, L prime plus vt1, divided by c. I'll take c on this side, and so from here I get immediately that T1 is equal to L prime over c minus v. Now let's calculate T2. So the photon has reached the right end over here and is moving back, but it doesn't have to travel all the way because that mirror has, this mirror over here has moved a distance vt2. And so what that means is that T2 will be L prime minus vt2 because the mirror has moved up. The light has to travel only this distance over here. And so from here, we get the result that T2 is equal to L prime divided by C plus V. Okay, so now we can calculate their sum, T1 plus T2. That's L prime divided by 1 over C minus V plus 1 over C plus V. And so it's easy to simplify. This is L prime into 2C divided by C squared minus V squared. And let's write this in a more convenient form. This is 2L prime over C into 1 over 1 minus V squared divided by C squared. But this 1 over 1 minus V squared over C squared, of course, is just gamma squared. So this is 2L prime over C into gamma squared. All right, but we already know that T prime is related to T through gamma T. Now this T is the proper time. It is the time that is observed by whoever is moving with the mirrors. So we have a formula for T prime here and a formula for T prime here. Let's put them equal. So we get gamma T equals 2L prime over C gamma squared. But remember that this T over here was 2L over C. That's the total time in the rest frame of the mirrors for the photon to go and to come back. And so from here, we can see immediately that we have gamma into 2L over C equals 2L prime over C into gamma squared. And now one of the gammas will cancel, the 2 over C will cancel. And so we have from here L prime is equal to L divided by gamma. Now this is the Lorentz contraction formula. It says that the length which is observed by the person standing on the ground will be the proper length divided by gamma. So since gamma is bigger than 1 or equal to 1 if the object is at rest, in that case L prime is going to be less than L. Hence you have the Lorentz contraction. Moving objects appear shortened. Let me quickly summarize what we've learned so far about Lorentz contraction. Objects moving along the direction of motion become shorter. So, if you have a rod of length L, which moves towards the right at speed v, then it will become shorter and have length L divided by gamma. Gamma, of course, is the usual gamma factor, 1 over square root of 1 minus v squared over c squared. On the other hand, nothing will happen to the transverse length. Why is that? I will leave the answer for you. Just use Einstein's postulate that all inertial frames are equivalent. Using that, you will see that the transverse length does not change. For this, you will have to devise a little experiment But as I said, I'll leave this up to you. We'll be able to get all the formula that we derive for length contraction and for time dilation once we have learned how to get the Lorentz transformation. Let me tell you what it is. Take an event. Let's call this event P. Now, in the inertial frame S, let's call this the frame S, an event would have coordinates t and x. So this is an event that happened at some time t, at some position x, as measured by s. This is another inertial frame. Let's call that s prime. It's moving this way with speed v, and that same event will have coordinates t prime and x prime. We shall assume that s and s prime are together when t equals 0 and t prime equals 0. Now earlier on, we had learnt about the Galilean transformation. In the Galilean transformation, t and t prime are exactly the same, and furthermore, x prime is equal to x minus vt. Now you can see how this comes about, because if you take this distance, which is x prime, well, x prime is this total distance minus this distance, which is vt. So the origin of s prime has moved away from s by an amount vt in time t. Now this is the Galilean transformation and will not hold when velocities are large, when v approaches c. So I'm going to rub this out. Instead, I'm going to make the assumption that x prime is some constant, I'll call that a1 times x plus a2 times t. And similarly, that t prime is equal to, let's say, a3 times x plus a4 times t. a1, a2, a3 and a4 are constants. What that means is that they cannot depend upon x and t, although they could depend upon v. This over here is also called a linear transformation. So if the coordinates of an event are known in frame S, you can get the coordinates in S prime. And of course, you can also go the other way, which means you could write x and t in terms of x prime and t prime. But we'll come to that later. Now I'm going to take a number of events. First, let me take the event P, which is equal to x equals 0, t. So that means that this event actually happens over here at time t, and now let's see what x prime is. Well, x prime is equal to a2t, and from here t prime is equal to a4t. Okay, now let's divide the two. So x prime divided by t prime is equal to a2 over a4. But x prime over t prime is the velocity of the origin of s. So according to someone in s prime, s is rushing in the negative direction with speed v. So this is equal to minus v. And so from here, we get a2 is equal to minus v a4. I repeat, we are looking from s prime at the origin of s, which is clearly moving in the negative direction, so moving in this direction, and x prime over t prime is therefore minus v, and so we got this relation. Now let's look at an event that happens at the origin of s prime. So That's an event P which is at x prime equal to 0 and happens at time t prime. Look again over here. Here x prime is 0, so 0 is a1x plus a2t. And from here, we obviously get x over t is equal to minus a2 divided by a1. But x over t is the speed at which s prime's origin is moving towards the right. And we've already said that that is v. So this is equal to v. And so from here, we get a2 is equal to minus a1v. We now have two relations. a2 is minus a1v and a2 is minus va4. And so we've arrived at the conclusion that a1 and a4 are equal. Now I'm going to take a third set of events. Imagine that when s and s prime were together, that is to say at t equal to 0, t prime equal to 0, there was a flash of light that was emitted from the origin. Well, that light moved out in the x direction at speed c. It also moved out in the x prime direction at speed c as well. Now, both these frames were together at t equal to 0. And so, we now consider that event in which x is equal to ct and x prime is equal to ct prime. That is to say, the speed of light in the s frame and in the s prime frame are exactly the same. We're now going to put in this condition and this condition into the above over here. So x prime is ct prime, and that's equal to a1 into ct plus a2 into t, and therefore ct prime is equal to a1c plus a2 into t. In this equation, I'll put a3 ct plus a4t, but a4 is the same as a1, and so t prime from here is a3c plus a1t. Okay, now let me divide this equation by this equation, and so I get c is equal to a1c plus a2 divided by a3c plus a1. If I take this on this side, then I have a1c on the left, and there's a1c over here, which will cancel. And so from here, I get a3 into c squared plus a1c equals a1c plus a2. Well, this and this cancel. And we know that a2 is minus a1v. So this over here is minus a1v. And that gives us a3 equals minus v over c squared times a1. All right, so we've made a lot of progress now. Let's simplify what we have over here. So now we've got x prime is equal to a1 into x plus a2 over a1 times t. But a2 over a1, that's minus v. So a1 into x minus vt, that's x prime. And t prime is a4 into t, but a4 and a1 are the same, as you saw from here. So we have a1 into t plus a3 into x. But a3, as we've just discovered, is minus v over c squared a1. And so here we have t minus v over c squared x. But what if you knew x prime and t prime How would you find x and t? The equivalence of inertial frames says that all you need to do is reverse the sign of v. So we should have x is the same constant a1 times x prime plus vt prime. So all I've done in this equation is change v into minus v. Similarly for the time, t should be a1 into t prime plus v over c squared times x prime. We now have a way of going from x and t to x prime and t prime. We also have a way from going from x prime and t prime to x and t. But we have one unknown constant a1 in terms of which all the others can be found. How do we find that? Well, we're going to do that by taking this x prime, which is a1x minus xvt, and putting in x and t from here. So x prime is a1 into x, and x is this. So that's a1 squared into x prime plus vt prime. Then there's minus v into t. So minus v into t times a1, so that's a1 squared v. And then t is given over here. That's t prime plus v over c squared x prime. Now you can see that a1 squared vt prime, this cancels with this. And so from here we have x prime is equal to a1 squared into x prime minus a1 squared v squared over c squared times x prime. And that immediately gives us that a1 squared is equal to 1 minus v squared over c squared to the minus 1. And so a1 is exactly what we had called gamma earlier. We've now found out the value of a1, which is gamma. In terms of a1, a2 is minus a1 times v. Then a4 is got from here and a3 from a1 itself. So the point is that in this transformation here we have found all the constants a1, a2, a3, a4. And we've also learned how to invert it. This was the basic form of the Lorentz transformation that we had started out with. We've now found out a1, a2, a3, a4 in terms of the velocity v, which is the speed at which the frame s prime moves according to s. Let me give a quick summary of the Lorentz transformation that we've just derived. There is a frame, let's call that s. We measure distances in the x direction here and in the time direction along the time axis. Some event happens. It happens obviously at some time and at some position. So its coordinates are t and x. Now suppose there's another frame which is moving towards the right at speed v. Then the coordinates in that frame, let's call it s prime, will be t prime and x prime. I repeat that both s and s prime are inertial frames. Now, in terms of this velocity v, we have the usual gamma factor, which is 1 over the square root of 1 minus v squared over c squared. And what we've just derived is how to go from x and t to x prime and to t prime. Suppose that v was very small compared to the speed of light. In that case, gamma would be close to 1, in which case x prime would be x minus vt and t prime would be just t, because you could neglect this. That, of course, is exactly the Galilean transformation. So the Lorentz transformation goes over into the Galilean transformation for small velocities. Now, if we want to go from x prime and t prime to x and t, notice that all you need to do is change v into minus v. And that's required because if you were to look from the point of view of s prime, you would see s as moving this way with speed v, that is to say, with velocity minus v. Now, these formulae are for one-dimensional motion. In general, you could have motion along any axis. It's actually quite easy to derive the most general form of the Lorentz transformation, but we won't do that right now. In this lecture, we saw how the coordinates of an event, as described in one inertial frame, can be related to the coordinates in another inertial frame. So the same event is described differently by the observers in two different inertial frames. This is, of course, the Lorentz transformation. In the next lecture, we're going to see how the Lorentz transformation leads to spectacular new predictions about physical phenomena.